Okay, so now we would like a last condition. And with this last condition, we want to define the strengths of interaction. And our intuition is coming from Coulomb's spheres. So remember, Coulomb measured the interaction of two spheres, one of charge Q, another of charge minus Q. It was two particles interacting. And also he had the particles were at rest. Okay, so these were the key ideas that I want you to keep in mind. And let's now see how to define it. Okay, so when we studied the two-point function, it was useful to consider the Fourier transform of the two-point function. Here, if we want two particles to interact, we want to create two particles, allow them to interact, and then later we want to destroy two particles. So it would make sense to study the four-point function. So we're going to now study the four-point function. And based on our experience with the two-point function, we're going to study the Fourier transform. Okay, we think that that would be a good thing to do. Okay, so what do we have? We have naught. It's the time-ordered correlator of four fields. So here we go. And then phi of x4. Good. And what will this be equal to? Well, we're taking a Fourier transform. So we have to integrate over four independent momenta. There's the third momentum. And now the fourth. And then we will have all of the exponentials. And then we will have a function of four variables. Now, actually, we know something about this function, and we know it because of momentum conservation. So we know that there's going to be a delta function. So here's our 2 pi to the 4 that goes with every delta function. And this is going to enforce that momentum is conserved. And this corresponds to having a delta function that sets the sum of the momenta to 0. If you are puzzled as to exactly why this is the correct way to implement momentum conservation, well, that's a perfectly reasonable question. In the next chapter, we're going to study this in some detail, okay? So we will look at this in a lot of detail. So suspend your curiosity for now. In the next chapter, we will really underline the piece that is, we will really derive the piece that is underlined in red. Okay, so now let's come down to exactly what object it is that we are interested in. So it's obviously going to be the 4-point function, okay? But actually, it's not the complete 4-point function. You see, remember what we had to do to calculate the 4-point function. What diagrams did we have to sum? So let me put some of them down. So you'll remember things like this. So we've dealt with this a few times. Those diagrams we summed. We also summed diagrams that looked like this, and it kept going. I don't know, let me put in a few more like that. And it just kept going like that, okay? And then we had terms that looked like this. So there was perhaps that. There was something that looked like this, and so on. And so it continued. Actually, if we take a look at where we have the two particles interacting, on the first line here, that doesn't correspond to the two particles interacting. It's the second time for which the two particles interact. And if we have to summarize this in a word, how can we describe these diagrams? Well, these are the connected Feynman diagrams. So these are the connected diagrams. So it's the connected diagrams that contain information about the interactions. So when we come to state our fourth condition, we will only sum the connected diagrams, okay? So just connected. Now, I want to remind you, what would the Feynman rule have been for this first term? Well, we would have had a minus I, we would have had a G, we would have had a 4 factorial, and then we would have had the 4 legs, okay? So we would have had, I'm going to only be schematic, but a G to the power of 4. Well, the interaction has got nothing to do with those 4 external legs. Those 4 external legs there do not tell us the strength about interaction. They tell us, you know, they're related to the amplitude for the particle to propagate from some point to the interaction point, and for the second particle to propagate from some point to the interaction point. But they're not telling us in any way about the interaction. So it makes sense to remove, or the word that people use is amputate, the external legs. These are not telling us about the coupling strengths. They're rather telling us about the amplitude for the particle to propagate from some space-time event to the interaction point. So we include a little prime here, and this means amputated, okay? So you've removed the external legs. So amputate. Amputated 4-point function, okay? So you've just removed the external legs. So if you were summing this in Feynman diagrams, well, let me try to indicate that. So I'll indicate there's the vertex, and these legs on the outside are little stumps because they have been amputated, okay? So just a stump of a leg, not a leg anymore. And then we would have, for example, this. These are internal lines, so those would still be there, but a little stump on the external lines. And so it would continue. So you'd add all of those diagrams, and then you set this equal to minus I G physical, GP, times by 4 factorial. Okay, so that's how we're going to define our coupling. But we're going to say a bit more. So we want to evaluate this where P1 plus P2 plus P3 plus P4 is equal to 0. And more than that, we want each of our momenta to satisfy the condition that P1 squared must be equal to P2 squared, equal to P3 squared, equal to P4 squared, equal to the physical mass squared. And then we also want that P1 plus P2 squared is equal to, oh, guys, sorry, I just want to change some of these signs, okay? It's just going to make our discussion slightly easier. I want to make this P3 and the P4 a minus. Inside the Green's function here, I want P3 and P4 to be minus. And here I'll have P1 plus P2 squared equal to 4MP squared. And then I will have P1 minus P3 squared equal to 0, equal to P1 minus P4 squared. Okay, so here what I've done is I have been quite specific in saying what momentum I want you to evaluate this correlator at. So I'd like to understand now, why are these conditions on the momentum needed? So that's what we're going to discuss now. Why are these conditions on the momentum needed? Okay, so let me tell you, so we're going to have the discussion down below. Let me tell you what these conditions are doing. And we'll do that by explicitly solving them. So let me tell you what set of momenta solve those conditions. Well, if we set P1 mu equal to, we'll put the energy equal to the physical mass, the momentum equal to 0, and we'll have this equal to P2 mu. And then we will also have the same form for the momentum for P3 and for P4. Okay, let's just check that this really solves it. Well, the conservation of momentum is saying that P1 mu plus P2 mu must be equal to P3 mu plus P4 mu. That's clearly obeyed. Okay, so this condition here, of course, was written for the 4 vector, the momentum 4 vector. So good. So energy and momentum are conserved. Obviously, all of these are on their mass shell. Sorry, this should be, I don't know why. Just watch me. Sometimes I do these weird things. This should have been a squared. Good. Okay. But now let's look at these. And I think that energy and momentum conservation, you understand well. I think that the mass shell, that the P squared equal to M squared condition, you understand well. Maybe the second line here is something that you don't, you're not so familiar with. So what is that telling us? Well, take a look. What that line is telling us, if we add P1 plus P2, well, we get 2 MP1 and naught for the 4 momentum. So if we work out what is this 4 vector squared, you know, it really is 4 MP squared. And it wouldn't have been 4 MP squared if we had a non-zero momentum. So this is occurring because the momentum is 0. And then when we say P1 minus P3, well, that is just naught, the null for momentum. And that's the same as P1 minus P4. So this is setting P1 and P3 to also have no velocity. So what these last conditions are setting, these conditions over here, they are making sure that our particles are at rest. But remember, that's precisely the conditions under which Coulomb measured the two-particle interaction. The particles were at rest. So that's what this condition on the momenta is doing. It is making sure that all of our particles are at rest. So this is the last condition that we need. This is the condition that tells us what the strength of the physical coupling is. So let's just copy this and add it to our conditions that we had written before. Okay, so this is our third condition. Good. Okay, so what you can see here is that with these 3 matching conditions, we now have 3 equations. You could go ahead, you have to calculate these correlation functions. So calculate them using the Feynman rules. Once you've got the 2-point function, take your Fourier transform, make sure its pole is at P squared is equal to the physical mass squared. So at that position that the experimentalist has measured as the mass squared, make sure that the residue of this pole is I. The residue of this pole is I. That I doesn't look very good. So let's make that residue I. Okay. And we read both of those, by the way, off of the renormalized propagator, which you see lined in green. It's got a pole at P squared is equal to MP squared and a residue of I. And then the third condition that we use is calculate the 4-point function, remove its external legs, so amputate the external legs. That's what the dash means. Keep only the connected piece. And whatever you get for that sum, set that equal to minus IG physical times 4 factorial. And the momenta must obey the conservation of energy and momentum, which I've underlined in green. You must obey this condition that P squared is equal to M squared. That's the usual condition from relativity, which I've underlined in red. And then that final condition on the momenta, which just tells us that the particles are at rest. And using those 3 equations, you can completely eliminate G, M, and Z in favor of the physical mass and the physical coupling. Great. Okay, so that's what I wanted to discuss in this chapter. I think let's discuss the exercises and just have a quick summary of what we achieved in this chapter.